For the past 40 years, astronomers have known that something about the cosmos doesn't add up. First in galaxy clusters, and then within individual galaxies, they found that visible matter, stars, gas, and dust, cannot account for the motions they observe. No one knows what this missing mass, now called dark matter, actually is. But studies by NASA's WMAP spacecraft of the cosmic microwave background, the oldest light in the universe, show how much is out there. Dark matter outnumbers ordinary matter by 4 to 1. The WMAP results also hint that dark matter likely takes the form of an as-yet undiscovered subatomic particle. WIMPs represent one hypothesized class of these particles. They neither absorb nor emit light and don't interact strongly with other particles, but when they encounter each other, they annihilate and make gamma rays. That's where NASA's Fermi Gamma Ray Space Telescope comes in. 2 years of scanning the sky with Fermi's Large Area Telescope have set the strongest limits yet for WIMP dark matter. The best place to look for gamma rays from dark matter annihilation? The most boring galaxies around, called dwarf spheroidals. These faint, tiny galaxies possess impressive amounts of dark matter, but they contain no gamma ray emitting objects and little gas or star formation. In the currently accepted cosmology, the first structures formed as the gravitation of dark matter corralled normal matter. Simulations show that the largest structures formed in this way were comparable to the dwarf spheroidal galaxies we see today. It's thought that large galaxies, like our own, were built up from collisions among these dwarfs. Using 2 years of data, Fermi scientists explored 10 dwarf galaxies for any sign of gamma rays from WIMP annihilation. In this graph, the dashed line marks the sweet spot where conventional expectations for WIMP dark matter align with what we know about our universe. Even when scientists combine all of the Fermi data from all 10 of the dwarfs, they see no sign of gamma rays. This limit shrinks the box where WIMP-based dark matter may be found, and, for the first time, shows that the cosmology we know essentially eliminates some WIMP types. The longer Fermi operates, the better its ability either to box in the nature of dark matter or to find actual evidence of what it is, and the discovery of new dwarf galaxies will make this search even more sensitive. Although nondescript, dwarf spheroidal galaxies may have been the first large structures to form in the universe. Now, they've taken center stage in the drama to solve one of astronomy's greatest mysteries.
Well, hello, everybody. This is Scott Roberts from Explore Scientific and the Explore Alliance, and this is number 70, the 70th Global Star Party. So up next is Doug Struble, one of the, I think, hands down, one of the world's best planetary nebula imagers. So, Doug, I'm going to turn the stage over to you, dude.
This is my main imaging telescope right here.
Awesome.
That looks like something Jason Gunzel
you have the field rotator on that, or how do you do that? So
that's so adorable.
That's what, a 20-inch refractor?
Yeah, you know.
Yeah, it's actually bigger than it looks.
Very
Apochromatic.
cool.
A triplet apochromatic.
Right.
Yeah, we're actually only as tall as halfway up the
That's right.
halfway
Right.
up the
Yeah, you can't
leg.
possibly reach the eyepiece without a really long ladder.
So,
all right, let's see what you've taken with it.
yeah, so there's this planetary nebula I
There's the
was going
observatory
after.
for it. Yeah.
Yeah, this is the Liverpool telescope in Spain, and I was going after a planetary nebula that was captured by it. And this is kind of what the Liverpool telescope came up with right here.
Okay.
Yeah.
Wow, look at that.
Yeah,
Look at that network. All those.
that's not mine. That's
Yeah,
what,
let's see how close you got. You usually
Yeah.
usually
Oh,
get
this
But
is-
look
dark
at this. Yours is
Oh,
better.
wow.
yeah.
Look at
That's
that.
excellent.
That's beautiful.
Yeah, so I took the Explorer Scientific 165 millimeter
Thank you, man.
in combination with ASI 183 mm,
There you
which
go.
has the smaller pixels, and my pixel scale is at 0.43 arc seconds per pixel,
Wow.
and I drizzled the data down to 0.215 arc seconds per pixel when I process this.
Oh man, that is beautiful.
So these stars that are in the background are actually like Mag 10, Mag 11,
Yeah,
Mag 12.
yeah.
So
Yeah.
there, if you, I take that toy telescope and think I'm gonna image it, it would not. You'd barely even be able to see the stars, let alone the planetary you got.
Yeah, exactly.
It looks like a toy telescope.
So what I tend to do, I tend to do a lot of planetary nebula. It works really well for me because in my Boreal sky scale of let me pull this up real quick here. This is actually my slide off roof in the back of the telescope here. I have two main rigs. My main rig is the Explorer Scientific 165 on that front rig there, and I'm using a 102 millimeter on my second rig.
Awesome. Do you like the roll-off roof type of observatory, or do you wish you had a domed observatory?
You know, I really love a roll-off, and the reason why is because a dome observatory only gives you one telescope to
True.
use.
Very true.
In fact, I want to put a third rig in my observatory if I can.
Mm-hmm.
Where are you located?
Unfortunately, I'm in Michigan, and this is
right there. See that really?
Yeah.
Oh, that's
crazy.
Detroit. Are you actually there? I thought you were a little further in the northern part of the lower thumb, Doug.
No, I'm in Taylor, which is 15 minutes.
Oh, okay.
Yeah, it's horrible. So I tend to do a lot of
So where I went to take that photo was in that thumb area of that other picture. There was someone that had a question earlier, Scott. That thumb area where it's darker, that's where I drove. But this is where your observatory is. Doug.
Yeah, check that out. Look, he's crying.
Yeah.
He's crying because his images are so awesome. That's why.
Oh, he's crying because look at the Bortle rating. It's Bortle 9.
It's more convenient for me because I own a multimedia company, so I have to work, and while I'm working, I'll set the telescopes, automated to do, certain things I'm focusing on. So I have a all sky cam below my two telescopes to watch the clouds and how my telescopes are reacting. And then on both rigs, I have a separate laptop to control each one of the two rigs, which I'm going after. So if you look at this particular diagram right here, this kind of gives you an inkling of what it looks like just with your naked eye.
Yep, I think I've seen every one of those.
I'm sure you have.
Yeah, from the 9 until I had gotten to 3 and going to Okie-Tex, I was finally able to see 1, and there is a huge difference there.
Oh, absolutely. So in my studio where I do a lot of commercial production, I also use my 2 Macs to process a lot of my data.
Oh, good. So that's mission control right there.
Yep. And then I have an IP camera I use to, control what I'm seeing throughout the night. And this is what I use for that.
I really have to point out that, you can take your astronomy way up the rung by putting an observatory either on your patio, your backyard. There's even a guy in Singapore who just aims a telescope outside of his window from his condo in Singapore. Okay. So you can imagine how light polluted that is. He polar aligned his mount inside of his bedroom. Okay. Aims it out of a glass window and does narrowband imaging, and it's unbelievable. It really is.
It's incredible. I mean, like, I think that, like, I remember when I was younger, my uncle, who was the one that really got me involved in this, my uncle Bob,
There it is.
back in the 80s, you had to live out somewhere remote, somewhere
Right.
where.
Well, that was kind of the mindset. If it wasn't like so dark, you forget it. Can't do really good astronomy. And I can remember so many amateur astronomers telling me, yeah, I would love to do it, but I can't get out of, I can't get away from my house. Light polluted here, and here we are.
I think you're close to your mic, Doug.
What's that?
I think you were a little close. You were close to your mic. We could hear you.
Oh, weird. Okay.
That's all right, but we can still hear you when you talk too. It sounds like you've improved your mic a lot over the last couple Zoom meetings in our Plymouth Astrophotography group. That mic sounds really good.
Yeah, the problem I have is that my speakers are equipped for doing multimedia production, so they tend to.
Right.
Yeah. So that's kind of what led me up to do planetary nebula. In this particular case, the oxygen overwhelms the hydrogen alpha, so I just concentrate on oxygen. This is another one I worked on recently, Able 30, or I'm sorry, Able 80. And this was composed mostly of hydrogen and oxygen data. And then this is
Look at that.
Able 79.
Now, after looking at Fornax galaxies and Sculptor galaxies with their barred spirals, this is really kind of hitting home right now.
We got the Barred Nebula.
Barred planetary nebula.
That's pretty good.
Yeah, the interesting thing about planetary nebula is, like, unlike a supernova, which has the mass to go particularly supernova, most of these stars don't have enough mass to go complete supernova. So you end up with something like this, where it's just blowing off a lot of gas, and usually it's hydrogen alpha and oxygen,
It's beautiful.
Thanks.
Do you know anything about distance of this object or other particular size?
Off the top of my head, I think, let me see here.
Pull it up. Let's see.
So this particular object is I'm trying to see how far it is away. Yeah, I don't have a particular distance on this particular object.
Abel 79. We can assist with that.
I heard that planetary nebulas sometimes are very difficult to measure distance to.
Yeah, I'm not seeing a value in the places I'm looking.
Yeah, it's interesting. And maybe it's because of the spectral, the redshift or, the spectral analysis of these things, but sometimes they're tricky,
Yeah.
Yep, doesn't say.
So, most of the time I tend to do planetary nebula because it works out really well for me here. They're small objects. They're usually in hydrogen alpha and oxygen, which I could pull off really well here with my light pollution. and they're still a challenge because some of them are pretty small, but with a lot of integration time, I can really hammer it.
Doug, I'm curious, did you just like stumble into it going, wow, that turned out really well? Or did you somehow know? What was the clues that led you to doing all this planetary work?
So the thing that led me into it was I still want a major challenge.
Sure.
I could do hydrogen alpha and O3, with a 3 nanometer filter like Astrodon, even with my light pollution here. But if I were to really go deep and do a lot of integration time, I could, there's still a big challenge. And then dealing with how small some of these are, it kind of levels the playing field a little bit in terms of what I can accomplish here.
I see.
Yeah.
But look how good the track. You're at. You're at a lot of magnification. Tracking is really spot on. This is really challenging. As far as getting images as compared to me using a tracker or something like that in wide field. I tend to be more in that range myself, so I know that.
I tend to go after really small objects because I can resolve some of the data really well.
Yeah.
By drizzling some of the data in PixInsight, and then by doing some extra sharpening, and other software packages,
Sure.
And then I'll do about an hour each of RGB for the stars, just to give it, the proper color for the star field.
Beautiful.
But I've been going after some older objects that I started out originally like a few years ago when I first got into this hobby, like in 2016, and in 2018 I started to get okay with it. Mm-hmm. So this is one I just went after recently.
Beautiful.
Yeah, wow, look at that.
Just beautiful.
It is.
And the bubble nebula.
Yeah. So like,
oh, that's cool. Right there.
So
yeah, you got that extra star forming region in there that I usually don't see in bubble nebula shots.
Psychedelic.
Yeah, I think you got to do it.
Here. I mean, it's crazy.
I think you got to do it in narrowband for it to really come out. Otherwise, it's just red like everything else.
And even with narrowband, usually that particular spot right there in the bubble is usually blown out. So I had to do a separate exposure for that, and then blend it in Photoshop.
Yeah,
beautiful.
And then another one I did recently was the tulip.
Yeah.
Unfortunately, I didn't get the bow shock outside the tulip, but I was more concerned with the back end texture.
Mm-hmm.
So that's kind of what I went after.
That's awesome.
And then I was reprocessing some data from earlier this year and did one at the California Nebula.
Oh, yeah, that's nice. That's a wider field for sure.
Yeah, that was done with a 70 millimeter.
Yeah.
In fact, that one in particular ended up in an astronomy magazine where I did like a show, Hubble palette version.
Yeah.
Great.
Nice. Congrats.
Yeah.
And then I did another one in Sky and Telescope with my sharpless 132.
Oh yeah, look at that. It's electric. It's beautiful.
Thanks.
Doug, what were kind of like the aha moments for you? I mean, everybody goes through this path, and they try until and there's a moment where things kind of click, and then boom, you got something that really shocks you or impresses you, as an astrophotographer. When were those moments for you, or what was one of those moments for you?
You know, the first moment for me, let me pull up this one image here. It was back in 2018, 2 years after I started astrophotography. And there was this one particular image I was going after called the Squid Nebula.
Yeah.
And I realized that you have to really hammer a lot of integration time with some of this stuff, you know?
Mm-hmm.
So yeah, let me pull this one up here. So this is my first image of the day on Astroben, where I really
That's squid.
Yeah.
That is definitely. Now you know why it's called the Squid Nebula. It's beautiful.
Yeah.
So ghostly looking against that red hydrogen and.
Yeah, it's a bipolar region, which you don't see a whole lot of when it comes to star formations.
Beautiful.
But that's when I really hammered out, and I realized after that point it just takes a lot of integration time.
Yeah.
And you know, it doesn't really matter where you live. I mean, like you can live in Arizona with some really nice skies, and you can get a lot of integration time in you know, you can get a really nice image in a short amount of integration time.
Mm-hmm.
But when you're going after some of these really faint objects, it doesn't really matter where you live. You know, you can live in Arizona, you can live in Michigan like me, and you know.
That would be a great article for you to write, because people don't understand that, right?
Oh.
Yeah,
that's really interesting. You know, that to get this fine of an image.
Yeah, I mean, there was an article I wrote for Scott in Explore Scientific a couple of years ago on Planetary Nebula.
Yeah.
And most of them are pretty faint. But it's a main focus of mine, not only because of what they are, but because I can do them successfully well where I live, you know, in narrowband.
Here, I'll
but also the talk
that.
of integration time. Do you see what I'm saying? To explain what that takes.
Yeah, absolutely. I mean, like, I think my longest one I ever did right here was this one right here. This is 106 hours.
Jeez. Wow. That's dedication.
Or if you do the math, you come up to about 4.5 Strubles.
4.5 Strubles, that's right.
Exactly.
Actually, I think it's 3.5. I overshot it.
Well,
yeah.
I mean, the interesting thing about this is it's two objects superimposed over each other. So you have a planetary nebula, NGC 40, and then the background you have CTA1, which is a supernova remnant, which is the part that's really faint in the background.
Yeah.
And that's kind of what I was going after. Unfortunately, during this time period, this was in August and July, where we had like a lot of forest fire smoke coming over, you know, pretty much the whole United States. So this background data would have came out a lot better, you know, if it wasn't for that, I believe.
Cesar Brolo is sending me a message right now. He says his connection, I probably because of the wind, I don't know, but his connection on the rooftop failed. So he's going to try to reconnect again, but we will, you know, if not, he's going to meet up with us next week. So.
Okay.
Yeah.
Good.
But this is great stuff. Beautiful stuff, Doug.
Thanks.
And I'm really happy you came onto the program.
Yeah, a lot of fun.
Yeah. Thank you.
Yeah. And you know, Scott, you got some good plugs for this was done with Explore Scientific gear.
Yeah, it was. I know. I when you see stuff like this, I mean, this is not stuff I could, you know, I do myself. Okay. So I'm constantly blown away by what amateur astronomers do with their equipment. And if, you know, if it happens to be some equipment that you built, then Wow, yeah, the feeling is really amazing. It is. So it's like watching a world champion skier use your skis or something like that, to break a record. And I would say that Doug is constantly broken records, certainly imaging from where he is. And I would say that whether you're amateur or professional, when you see Doug's work, you're seeing some really amazing stuff that's beautiful. So
And
thank you.
some, and I call it easy dedication. Obviously, Doug, you're very dedicated to, you're processing this stuff over a lot of time, and you've got your processing, your workflow down. And it takes all of this time. It's not something that you can just snap out in a 2-second image, which is, I have the shortest integration time in all of my images, 30 seconds. That's called a Bradley. You get something in 30 seconds, but it's the opposite of the spectrum.
Right.
It's like, I can't
Inverse
wait.
Struble.
Yeah.
I know, and most people, when I post an image, they think like, "Oh, I took a picture in the galaxy."
Right. No.
And that was it.
No. All of the and we've got, there's astrophotographers that are in our group that approach 30 hours. They're pulling out images with 10 hours of time and 15 hours of time, and then they begin to approach some of the intricate detail. And you can get a basic shape of something, you can go somewhere dark, like that Crab Nebula right there. You can look at that Crab Nebula, you can look at a Hubble image of it, and you can begin to see some of the same detail that it takes Hubble. Maybe it'll take Hubble maybe a little less time to get it because of its position in space, but you're seeing detail that you could only see looking at professionally used telescopes.
Look at that.
Yeah, I mean, the bottom of the line is like, you can have some of the best processing skills there is, but you're not going to pull out. There's no substitute for long integration time.
Mm-hmm.
Yeah. And I think Gary, one of the other astrophotographers here, and he's saying the same thing, which is why I'm looking at, if I want to do a little bit of deeper work, no matter how dark the skies I travel to, being able to get longer times just seems to make a huge difference. The image of the Orion Nebula that I got in 2 minutes without a modded camera just sort of showed me, well, if you can point at something for a long enough time, all of that light comes down into the sensor, gets trapped, and now you have more data to work with. So it's just something I see your work, Doug, and it's like, eventually I got to get, I've got the 30-second thing down pat. I'm going to have to, work on that, getting longer if I want more detail. It's part of the process as it goes. So it's awesome. It's always a real reminder of it when we see your images.
Mm-hmm.
Yeah, I mean, we're fighting atmospheric distortion essentially.
Yeah.
That along with light pollution, what have you. So.
Yeah, and I was gonna, one of the things, the proponents of light pollution, we talk about losing our skies. Visually, you lose your skies. You don't want to get to the point where the only way you can see this is through, although that would probably make you very happily employed, Doug.
Right.
But it takes all of that time to see these things in space. So there's still a battle to keep light pollution from forcing our hand with this, but it's also not as easy. We've been talking about, it's not as easy as just take a picture and you've got something as intricate as this. So that's definitely definitely a lesson for myself and a lot of us that like to do astrophotography.
No, and I've done some broadband stuff before, like this one right here.
Yeah.
I just really had to pile on the integration time to pull something like that out,
Yeah, and just seeing the detail you've got over here, with I think this is 51B basically. I forget which one is A and which one's B, but in most images this is almost nothing. It's just kind of a wisp, and you see some detail in the galaxy, the spiral, but in yours you've got detail in the secondary galaxy here that's interacting with it.
Yeah.
So that's, you know, that these subtle little things that always draw my eye, and it's you want accuracy as well as, you know, you have a pretty picture here, but you've got it extremely accurate too. You know, you could almost do a little bit of science, I would imagine, with an image that's, you know, that's got that much accuracy in it.
Yeah.
Thank you very much, guys. That's great.